Hello fellow science teachers, welcome to my very brief overview of the chemical sciences in the Australian Science Curriculum and Early Years Learning Framework. I've got a question for you. What did you learn in chemistry at school and how did you learn it? Was it fun? Boring? Do you remember being curious? Did you learn about atoms and chemicals and electrons? Let's see if we can make it a bit more interesting this time. Thank you to Wikipedia for much of the art in this presentation. Now let's see the big idea. Every strand of the curriculum has one or two really big ideas that tie the whole strand together. And when it comes to the chemistry curriculum, you cannot understand what's happening in chemical reactions until you understand about atoms. But I have a bit of a problem. It's not until year 8 or 9 in the current Australian curriculum that we start to talk about atoms. Maybe it should be in grade 3. Here's the year 8 and 9, and that's when we finally actually use words directly related to atoms, like elements and compounds and mixtures. Take a quick look here in grade 3. The physical sciences, chemical sciences, are both talking about heat. I figure there's space there to talk about atoms. Your kids are going to love it. Once we start talking about atoms, we're talking about the largest orbs we can imagine, stars and planets, and we're talking about the smallest orbs we can imagine, or the atoms that make up the whole universe. So that's my thought on the matter. You're a professional now, so you are allowed to have an opinion on such matters, on what ought to be in the curriculum, how it should fit, how it's going to fit in. Time to have an educated opinion on such. So, what are these atoms of which I speak? Strange little entities in the universe. So what's stuff made of, according to science? Well, this is a very old question. From about 2,500 years ago, ancient Greek philosophers were asking what everything's made of. You remember some of the original ideas, earth, air, fire, water. Well, one of the many questions they had is, if you take a piece of metal and break it in half, you've still got metal. Well, can you break it in half forever? You'll always have a smaller and smaller piece of metal, or to eventually get to a piece that you can't break anymore. And a scientist known as Democritus really scientified that idea, put it together for us to keep. And we don't know what he looked like, but here's a picture from descriptions. He's laughing because he loved to have a joke. He's wearing ancient Greek clothes and he loved to travel, so he's near a picture of the world. But his idea about atoms, he called them atoms, which in his language meant unbreakable things. So they'd have to be small, shaped. Maybe the spicy lemons were spiky little atoms and oil was round and smooth because it was slippery and such. But he had a problem most scientists have, is that he couldn't test his theory. It was a great idea, but they had no way to test things that were so incredibly small. So after about 2,000 years, 1,400 years or so, began to appear that there were some things which couldn't chemically be broken, like water. Can you break it? Well, if you put lightning into it, it breaks into hydrogen and oxygen. And you can't chemically break hydrogen and oxygen any further. And you take a tree, you burn it, it breaks down into soot. And you can't break that carbon down chemically any further. So after about 1,400 years, it began to look like there are a number of substances which couldn't be broken. They began to think Democritus could be right. The universe is made up of these little atoms, which is all well and good. They found dozens of them. Not a lot to go with. By the 1800s, we were heading towards approximately 63 different kinds of atoms which we could count. Couldn't be chemically broken up anymore. We're very happy to use them there. But what did they look like? That was the question. Now, John Dalton was an English chemist in the 1700s. Really developed some good ideas around atoms. Element is a material with only one kind of atom within it, and all atoms are the same element, of the same size, and have many of the same properties, so you can recognize them one from another. He thought atoms couldn't be divided, and they could not be created or destroyed. They were already in the universe, ready to be used. And in chemical reactions, atoms are combined, separated, or rearranged. But once again, he didn't really have a good idea of what they look like. Now, by about the 1800s, people had started to organise the atoms into groups and tables, but it was very difficult for them. They couldn't quite figure out how they all related to each other until Dmitry Mendeleev came along, a Russian chemist, and while he was writing a textbook, he came up with the idea of arranging these in sort of periods, which is where we got the periodic table of the elements. He says he came up with the idea apparently in a dream. As I saw in a dream, a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary, which is an interesting way to do science. The important point here is once he wrote it down, he was able to test it. One of the great things he did in his periodic table, hello Dmitry, is he left gaps. Here's a Russian postage stamp commemorating Mendeleev. We've got gaps, little question marks, where he's suggesting we might find an element. And these are what some of its properties would be. This is great science. He not only had a theory, but he left predictions that we could test. Later on, and very shortly afterwards, testing those ideas, we did find the elements which he had proposed belong there. So Dmitry helped to expand what we know. So now we're left with quite a few elements to work with. Approximately 94 are naturally occurring. Elements are materials with only one kind of atom in them, such as iron. This is some pure iron. We've got some carbon. Interesting, here we've got coal and diamonds, both only carbon atoms, just arranged differently. And in a diamond, it's packed together in little tetrahedral shapes incredibly strongly and powerfully. We've got oxygen. This is liquid oxygen, cooled down to a very, very low temperature so that it condenses and forms into a liquid. Funny liquid, this stuff. It's cold enough to give you frostbite, but if you pour it on anything, including wood, it starts to catch fire because oxygen loves to react with things. Weird stuff. This is a piece of uranium. Incredibly dense material. And the current periodic table of the elements. Perhaps you've seen it before. We've got the periods here, the 7 of them that make up the table. And you know these little guys down the bottom? That's because they actually belong right here in period 6 and 7, but they don't fit or else the table goes well and truly over the page. Not to worry though. Some more fun with the periodic table is we have a couple of groups. These are the alkali metals, the first column, lithium, sodium, potassium. These metals are highly reactive and produce alkaline substances when they react with water. And then it that's sodium in water. Here we've got the alkali earth metals, second column. It includes magnesium, calcium, barium. These metals are less reactive, but they're usually found alone in nature. These are mostly transition metals and a few of the other interesting materials that make up the world. We'll skip to these guys here. Second last column. These are dangerous. They have to react with a lot of different things. The halogens, and last we have the noble gases. The 18th column includes argon, neon, krypton, odorless, colourless, tasteless, noble because they don't react with anything. But we find those in the often in glowing lights because they don't react. They can last a good long time. This is another way to draw the periodic table. Perhaps you find this more youthful. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, fluorine, neon. You can see they're all, once again, here in their groups, and each circuit is a period. Is that a better way for you to remember it? Perhaps there's another way. Let's try this, this beautiful table, helping you to understand the relationship between the elements, different ways in which we can display the same periodic table, which is the list of all the elements of which we are aware. And this wacky table, which is purely designed in terms of relative abundance, how much hydrogen, aluminium and silicon there is, fairly large amounts, and much more smaller amounts of things like hafnium and uranium. Interesting way to display the table. I thought I'd share it. So, Dmitry helped us organise the atoms, but the question still remained of what they looked like. Now let me introduce you to J.J. Thomson. Now, he was a clever British scientist who really started to get going the discussion of what he thought atoms looked like. the electron, deciding that atoms weren't unbreakable, you could rip off the outside layer of them. We thought atoms might be round, like this ball, with lots of positive charges and little negative electrical charges which could be pulled off and move around to create things like static electricity. So that was his theory of what atoms look like. Little plum puddings, what do you think? A plum pudding model. Now I'd like to introduce you to Ernie. Sorry, that would be Baron Ernest Rutherford, a New Zealand-born physicist and chemist, one of the great experimenters of the 20th century. He did an interesting experiment. Have you ever got a ball and thrown it at a wall and it usually bounces back? Well, he did that with atoms, gold foil and helium atoms, and most of them went through. And he was puzzling and puzzling till his puzzler was sore. Why were they going through? Were there holes in the atoms? And he decided that indeed there were. So while JJ had a plum pudding model, Rutherford posited that atoms were mostly empty space. What this would mean if you compress all your little nucleuses in your body down within all your atoms. There's less than a teaspoonful worth of the stuff that makes up you. Still weigh the same amount though. This led to another scientist, Danish physicist Niels Bohr, who came up with what we call the planetary model of the atom. See, mostly empty space. You've also got this 3D model which I created here, so other atoms can pass through fairly easily. Only occasionally do they strike the middle nucleus and then bounce straight off. This is the most common model of the atom that we have. It's conceptually easy to understand. Bohr's planetary model of the atom is reasonably conceptually easy to understand. It's easy to picture. It's very successful explaining things. Bohr was able to use it to explain the phenomenon of atoms glowing and lighting up as the electrons jump from higher to lower energy shells. So, slightly inaccurate as this picture is, it's the planetary model of the atom. It's the one you and I are typically most familiar with. Now, this is one of the main points in the history of science where chemistry and physics divide, because you can't teach one body of science without teaching everything else that science knows. It all fits together like a body, a bit like the monster from Frankenstein's monster. Sometimes it doesn't fit together well and the stitching's a bit messy, but science fits, it belongs together. And we'll talk more about that later. Now, about this time, Schrödinger comes along, an Austrian-Irish physicist who did an interesting contribution, some huge contributions to science, particularly showing that electrons aren't dots like billiard balls. They're more like waves. They can be in multiple places at the same time. Along comes Heisenberg shortly after, a German theoretical physicist, publishing his work in 1925 and come up with quantum mechanics. Einstein, another great scientist at the time, hated quantum mechanics, but his criticism, Einstein's later criticisms of quantum mechanics really helped bring out the best in quantum mechanics. It passed the test, the toughest test that Einstein could throw at it. But the Heisenberg atom looks even weirder. Heisenberg was talking about how observation is now mixed up with the nature of reality, and we can't separate the two, even in physics. A whole interesting line of reasoning behind that. It's well worth your time looking into. Quantum dynamic model of the atom is stranger still. You end up with places where the electron might be, depending on how you look at it, nodes where the electron's not going to be very much, and the antinodes where the bright peaks of the wave where the electrons are most likely to be. You end up with strange little patterns. Hydrogen wave function. Here's one I prepared earlier. These balloons representing where the electron might be depending on how and when you look at it. Really weird pictures of atoms. So let me ask you, is this what the atom looks like? Where does this madness end? What do atoms really look like? Why does no one really know? And we can end up screaming into the abyss. But perhaps there is a moral to this story. Maybe you will one day be the scientist who creates the newest, most effective model of the atom. My point is we're still learning. We're not done. There is still more to know. So if we're going to teach chemistry, we have to teach about atoms and teach them with not exactly sure what they look like. There's so much we don't know. I mean, electrons are weird enough. And then you get protons and neutrons and little quarks and antiquarks. There's a lot we don't yet know, but that is the nature of science. Spectrometry is seeing atoms, and we can have some good fun with that. Of course, you're seeing atoms whenever you look at me because I'm made out of atoms. But here's a few flame tests that you can do. Copper, strontium, potassium and sodium, different colours that show up when you spray one kind of atom into a fire to make it hot enough to glow. The little electrons in the shells jump between higher and lower levels, and as they do, they emit a very specific colour specific to each atom, and so you can tell exactly what atom you've got by what colour it is. This, for instance, is how we know what the sun is made out of. We've never been to the sun and got a teaspoon of sun before. The only way we know is by the colour that comes to us. And when we make something here on Earth exactly the same colour, we can say the sun is mostly hydrogen, a little bit of helium, and just about a little bit of everything else. All from colour. Spectrometry is one way to know what atoms you've got in a substance. So let's break it up a little bit. Some language is going to be helpful. We've touched on elements. Atoms of their element argon exist on their own, or oxygen. This is oxygen in the atmosphere, O2. So another pure element, just one atom in the material. A diamond is an element of carbon. Then we've got compounds once the atoms begin to rearrange. This is carbon dioxide. Carbon, which we see as that black soot, and oxygen, which is that blue liquid, and they mix together and they just form carbon dioxide, which you can't see, but it's fizzy. It's fizzy on your tongue, it's fizzy up your nose, it's fizzy on your eyeballs. Carbon dioxide's pretty useful stuff. Though I'm thinking that's not a great picture because CO2 is a straight line molecule, not a bent one. That's more like a depiction of water, H2O, with blue oxygen and two little hydrogens around the edge. Atoms get really weird when you start to mix them together. Take table salt, for instance. Great fun stuff. Sodium chloride. Sodium's a silver metal that explodes when you throw it in water. And chlorine is a brownish green gas that if you breathe it in will kill you painfully. Put it together and you get table salt. Atoms are amazing things when you mix them together. And then we have mixtures. These are helpful little things, which is just all the different materials mixed in together. Most substances are mixtures. Now let's pop into the curriculum and take a quick look at what we've got to learn. This is the Early Years Learning Framework, 4.1. Children developing curiosity, which is something kids are really good at. And 4.2, a range of skills such as experimentation, hypothesizing, researching and investigating. Children, I said, already do this. It's about naming it, make it useful, verbal and conscious, breaking it down into steps and finding ways to represent it through graphs, charts and tables. Science is really fun in the early years. A very natural time for science to happen. And some of the best sciences I've ever seen is happening in kindergartens. So let's talk about what the Australian curriculum looks like. A very brief overview at this point. Lots of details, lots of elaboration, lots of resources online that you can check out. So let's take a quick look. Firstly, we start in the foundation year levels, which is prep, talking 5-year-olds. Recognise that objects can be composed of different materials and describe the observable properties of those materials. So we're talking about things like sorting and grouping materials based on observed properties, using digital cameras to do a scavenger hunt, and suggesting the use of different materials like wire saucepans made out of metal and such. So generally very direct sensory experiences with materials. Now, we do skip grade 1, mostly perhaps because we have a crowded curriculum already. Go straight to grade 2. Recognise that materials can be changed physically without changing their material composition, and explore the effect of different actions on materials, including bending, twisting, stretching and breaking into smaller pieces. So this is a fun year. We're talking 7-year-olds. We're getting to get them to talk about The use of materials, how they can be changed, build parachutes for little egg gliders and such, manipulating materials such as paper and fabric, seeing how things different, the properties of materials change when you change their shape and composition and temperature and such, crushing a stick of chalk into powder and then using it, whether it's the same material. One activity which I do not advise is if you break most materials into small powder, you can set them on fire. It's called conflagration. Worth checking out if you've got a group that you love to demonstrate fire to. And exploring First Nations making physical changes to materials to produce such objects as bowls, baskets and various fibre crafts. Great opportunity to get your Indigenous curriculum and your Indigenous visitors in to show them how they use materials. A fascinating use of materials right under our feet here in Australia. We go down to grade 3. We're talking changes of state, which is also in the physics curriculum, but we'll move on. I mean, you could throw in discussion about atoms here. It's pretty worthwhile. Identifying and naming materials in the classroom, naming the materials that make up the objects in the classroom. Identifying familiar objects such as shoes, drink and backpack, and examining what materials they're made from. Suggest reasons why they have those different materials. So yeah, really good chance to talk about atoms, how they make things up. And there's a great chance for doing, and I don't advise this, but doing spectroscopy, setting fire to things like copper sulfate to see green fire, demonstrate green fire. Maybe not use an activity for the kids. But we'll see what you can get past the school management. Let's go visit grade 4 now, examining the properties of natural and man-made materials. So here we start to talk synthetics, really get into what has been produced by nature and what has been augmented by humanity. Explore examples that demonstrate gases have mass. This is a really fun one. Air has pressure and such. Blowing air through straws to move objects using balance to compare empty balloon one filled with air. And my personal fun is you get a cup with tissue paper just rammed in there and you put into water, and the water does not get into the cup because the air is keeping it out. Air has pressure. Air takes up space. So much fun stuff you can talk about that. Start to talk about the model arrangement and particle motion of particles in solids, liquids and gases, and virtual demonstration of coloured gases being compressed and provide explanation for the change in colour intensity. Really fun activities here you can get, such as melting coloured ice cubes and watching the material move, the coloured material move through the rest of the liquid. How's it looking?
Whoa!
Now,
It even made it look like a volcano.
It sure does. That's a magma lamp, and as the water fills with air bubbles, it lifts it up and off it goes. Turn it around so we can see. When the water gets to the top, it pops. And the water becomes dense enough for it to sink again. There we go, look at that. A perfect little magma lamp. So much great stuff here that you can do in year 4. Then we get to year 5, which is explaining observable properties of solids, liquids and gases by modelling the motion and arrangement of particles. So year 5, we're focused on heat and how things move. We're talking about things like gases having mass, which is a lot of fun. You could blow up a balloon and see how much the water lifts it up due to water pressure. Hydraulics is a great fun thing to do with liquids, for instance. And magnetism is a property of certain solids and liquids. Great stuff to discuss. Year 6, comparing reversible and irreversible change. Now, this is really important. We're starting to get into recycling in this year level. We want to sort our materials properly. We want to understand what changes can be reversed, which ones can't be. Examining the substances produced in cooking and rusting compared with their original substances, and dissolving substances in other materials. So it's important questions to ask here. Investigating first Australians' knowledge of reversible processes such as the application of adhesives and irreversible processes such as the use of fuels for torches. So it's a pretty meaningful year this year in grade 6. We've come to understand materials and now we get to know them better. Of course, there's always heaps of fun, like playing with oobleck or making gack. And now we get to year 7. We're talking about using particle theory. Finally, get to draw different representations between pure substances and mixtures, identifying the different solutions and the solvent and the solute. Great chance to mix chemicals together like putting sugar or salt in water, and you can still taste the chemicals there even though it's invisible. Then you can use different techniques such as filtration, decantation and evaporation. Evaporate your little cup of sugar or salt, the water departs, so you end up with crystals of salt or sugar. Great way to get into a discussion about geography and geology and where stones and crystals come from. Explore separation methods such as in the home recycling, putting the recyclables in the right place, analysing the physical properties in mixtures such as size, density and volatility, which is whether or not it's likely to explode. Important discussion with certain recycled projects as well. And First Nations separation techniques such as hand picking, sieving, winnowing, yandying, filtering, cold pressing and steam distilling. Great techniques used by the people of Indigenous Australia. Techniques we still use. Year 8, classify elements, matter as elements, compounds or mixtures and do models of that. Sounds a bit boring, but we are talking about some fun stuff here. We can talk about very much the discussion we've had so far today about Dmitry Mendeleev and the story of the history of the atom, the arrangement of the periodic table and questions we have regarding that. And of course, you wouldn't want to miss out on your chance to do some spectroscopy, set fire to some things, show how different materials have different colours. And then we'll skip on to year 9, which is always a fun year. We're focusing here on the actual model of the atom. We're breaking it down. Unlike Democritus originally thought, atom meant indivisible. Well, we found that you can divise them. You can smash atoms apart, and they have 3 major ingredients: protons, neutrons and electrons. And there's so much we don't know about those things and how they work yet. We're still discovering so many new things. So there's lots of questions. But the fun thing you get into here in year 9 is radioactivity, X-rays, and things like carbon dating. So you can examine timescales far wider than any one human life can experience. History of the universe and the placement of fossils in the historical record, and how we can date native Australians back to currently 60,000 years or more, having lived in this country. And of course, using radioactivity in medicine. So lots of practical things have come about from our knowledge about the divisible atom. So what's the point? Some of the key ideas. Chemistry teaches us that matter cannot be created or destroyed, only changed. This sounds pretty profound, but it's an ancient belief which stayed around. The idea is you don't make matter, it's already there in the universe. You can change it from one state to another, but you don't make it or destroy it. We're starting to push the limits of that understanding, but it's important to remember whenever you mix 2 chemicals, there's the same amount of chemicals before as there is after. Whenever you digest food, there's the same amount of atoms that go out of you as you brought into you. It's a fascinating thing about chemicals. Law of conservation of mass underpins all modern chemistry. In a certain sense it's wrong because you can change mass into energy, but that's physics in the upper year levels. We credit Antoine Lavoisier, who's French, who expressed the conclusion in 1773, and which is a point you can really see from the discussion I've had today. People from all different cultures have contributed to our understanding of science. They talk about people from New Zealand and France and England helping us understand about what atoms are and what they look like and how chemistry works. There's so much to learn. Now, the difference between physical and chemical changes. In physical changes, matter changes form, but the chemicals aren't changing. So if you chop wood, you've still got wood before and after. Melting ice, you've still got water. It's just a solid or a liquid. Mixing grey and green marble, shredding paper, the same materials before and after. In a chemical change, you end up with new chemicals. When you burn wood, you start it with wood, you end up with carbon dioxide and water and soot. Rotting bananas, mixing vinegar and baking soda, new chemicals are made in a chemical change. Now, I have on my website a whole host of fun activities to do with chemical changes: volcano mix, red cabbage indicator, sherbet, Electroplating, to name a few. There's just as many with physical change as well. Dry ice, sifting, blowing bubbles, mixing oil and water. Really, so many fun things you can do with physical and chemical changes. Now, natural versus synthetic materials. Natural materials like chalk, sand and oil. Man-made materials such as concrete, glass and nylon. We need both materials to survive in a modern society. We need to make good use of our resources too. I often think that we don't throw things away. We're merely storing it in a dirty hole in the ground until we can figure out what to do with it. Until we get to 100% recycling, we're leaving our mess for someone else to clean up. Reversible versus irreversible chemical changes. Now, reversible changes, such as states of matter, whereas irreversible changes are things like burning, rusting, heating and mixing. Make sure you stop off and chat to me if you've got more questions. There's some really interesting activities online that you can find anywhere about reversible and irreversible change. So I hope you've enjoyed our very quick introduction to the chemistry curriculum. I have great confidence in your ability to go online and find some activities that really nail down the sort of fun that you want to have with your kids. Remember, you've barely got an hour a week for science, so if you want to really get into any activity, you're going to have to do a little bit of cross-curriculum work, throw in some maths, build a table, get the kids to draw, build in some art. Only by using your cross-curriculum priorities can you have enough time to do some really fun activities and experiments with your kids. And remember, probably the most important thing is when I edit the peer-reviewed journal articles which get sent to me, if the researchers are any good, they start with a question, but if they're really good, they end up with more questions than they began with. If you're going to have some fun activities with the kids, that's something to keep in mind. See if you can help them end up with more questions at the end than they started with. It's one way to know they've engaged. It's one way to know they've had fun. It's one way to know what you want to teach them next. Thank you for your time.